What makes an orthonormal basis better than a regular basis? In today's video, we will talk about what an orthonormal basis is, why it is better than a regular basis, and how we can turn a basis that is not orthonormal into one that is. There are three parts to the definition of an orthonormal basis. First of all, every vector in the set is orthogonal to all the other vectors. Geometrically, this can be thought of as the vectors being 90 degrees from each other. Secondly, we also require that each vector in the set is of length 1. And finally, we require the set to be a basis. We will be defining the first two of these based on the dot product. The dot product is applied to two vectors and the result is a scalar. To take the dot product of two vectors, you multiply each component of the two vectors and add it all up. The dot product also has some nice properties, like the fact that it's distributive. We can use this to define the length of a vector. We will define the length of a vector as the square root of the vector dotted with itself. We call this the norm of the vector. You will sometimes see this written as the norm of a vector, but more often it will be written as a vector surrounded by two vertical bars on both sides. Using the dot product might seem like an odd way to define the length of a vector, but it should look familiar if you've ever found the length of a vector using the Pythagorean theorem. This definition is actually the same as adding the square of each component and then taking the square root. Now, with the length of the vector, we can define what it means for a vector to be normal. We say that a vector is normal if its length is equal to 1. We will also be defining orthogonality based on the dot product, but for that, we need to define the angle between two vectors. We will define the cosine of the angle between two vectors to be equal to the dot product of the vectors divided by their lengths. We want orthogonal vectors to have an angle of 90 degrees between them. This means the cosine of the angle is equal to 0. For this to be true, it must be the case that the dot product of the two vectors is equal to 0. So this is how we will define orthogonality. We will say two vectors are orthogonal if they have a dot product of 0. Now, with these definitions, we can define an orthonormal basis. To recap, all of the vectors in the basis are orthogonal to each other. So, if we take any two distinct vectors from this set, their dot product will be 0. Also, all vectors in an orthonormal basis have length 1, which means any vector from the basis dotted with itself will equal 1. We are requiring such specific properties from these vectors, but why should we even care about such bases? There are many reasons to prefer an orthonormal basis over any other basis, but I will just be talking about one of the reasons. Orthonormal bases make for quote-unquote nice coordinate systems. More specifically, they make it easier to find coordinate vectors. In case you aren't familiar with coordinate vectors, a coordinate vector is a vector that contains the coefficients of the linear combination required to get that vector with respect to a specific basis. Usually, finding the coordinate vectors can be difficult and often involves solving a system of linear equations. This gets even more difficult the more components a vector has. Finding coordinate vectors with respect to an orthonormal basis is much easier. Let's see why. Suppose we have an orthonormal basis, beta, and a vector x. X can be written as a linear combination of the vectors in beta. So, x equals a1 times v1 plus up to some ai times vi, plus all the way up to an an times vn. We are interested in finding the coefficients. Now, let's see what happens when we take the dot product with vi on both sides. On the right side, we can distribute this out. Vi dotted with vi will equal 1 because it is normal. The dot product for all the other vectors will be 0 because the vectors are orthogonal to vi. So x dotted with vi is equal to ai. This means the ith component of the coordinate vector for x is x dotted with the ith basis vector. So the coordinate vector for x with respect to beta is x dotted with each of the basis vectors in beta. This is much easier than before, but this is of no use if our basis isn't orthonormal. To be able to use this for other bases, we want to find a way to turn any basis into an orthonormal one. Assume we have a basis that we want to turn orthonormal. The easy part will be turning it into a basis with vectors of length 1. This is known as normalizing our vectors. To do this, we can divide each vector by its length. Doing this for each vector makes sure that it has length 1. This also works for vectors which have a length of less than 1. Now, for the slightly more challenging part, turning our basis into an orthogonal one. One way we can approach this is by creating a whole new basis. Then, we can put in our original basis vectors one by one, but only the parts which are orthogonal to the vectors already in the basis. Assume we have a basis beta. We will be building our new orthogonal basis gamma. We can let the first vector v1 into gamma, and let's call it u1. For our next vector, v2, we only want to include the component of v2, which is orthogonal to u1. So, we will subtract the part of v2, which goes in the same direction as u1. Let's think about this geometrically. This is u1, and this vector here is v2. There's a component of v2 which is parallel to u1. You can think of this as the shadow of v2 onto u1, from a light that is infinitely far away. If we subtract this from v2, we will get a vector that is orthogonal to u1. This is perfect. Now, we can call that new vector u2 and add it into our new basis. If we were working in a higher dimensional vector space, we would just need to repeat these steps for all the other vectors until we have built an orthogonal basis. But since we are in R2, we can stop here. This is all good in theory, but we need to know how to actually calculate this. We need a way to find the parallel component of a vector with another vector, and to do this, we need to take a closer look at the dot product. Earlier, we talked about how to calculate the dot product, but it turns out it also has a nice geometric representation. If we have two vectors, u and v, and we take their dot product, we will get the length of the vector, which is the projection of u onto v, multiplied by the length of v. Quite surprisingly, this is the same as the length of v projected onto u, multiplied by the length of u. But for now, we will focus on u being projected onto v. This will be written out as proj of v onto u. Here, u will be projected onto v. Since u dot v is equal to the length of u projected onto v times the length of v, dividing by the length of v on both sides will give us just the length of u being projected onto v. Now, we need a vector of this length which goes in the direction of v. We can normalize v, which means v will divide it by its length. Now, we can use this to get our desired vector. Overall, we dotted u and v divided by the length of v squared. The length of v is just the square root of v dotted with itself, and it is being squared, so it will just be v dotted with v. So, this will be our formula for a vector being projected onto another. Now, we can use this to get back to orthogonalizing a basis. Now that we have a formula that lets us find the projection of a vector onto another, we can explicitly write out how we would turn a non-orthogonal basis into an orthogonal one. Once again, we have a non-orthogonal beta with vectors v1 through vn. We are looking to convert this into orthogonal vectors u1 up to un. We will let u1 just equal v1. Now, for u2, we will start at v2. And then we need to remove the component of v2 which goes in the same direction as u1. We will project v2 onto u1, which gives us the part of v2 which is parallel to u1. Then we subtract that from v2 to get a vector orthogonal to u1. Similarly, for u3, we will start at v3, then subtract v3 projected onto u1, and then v3 projected onto u2. This vector will be orthogonal to both u1 and u2. Make sure you are projecting onto u1 and u2. We need to make the new vector orthogonal to all the vectors in the new basis we're building. We can repeat this pattern for all other vectors. Generally, we can write this as un is equal to vn minus the sum from k equals 1 to n minus 1 of vn being projected onto uk. We can also replace this with the formula we found for projections to get a more explicit formula. After repeating this on all the vectors, you should end up with vectors that are all orthogonal to one another. The final step to turn this into an orthonormal basis is to normalize all of the vectors. As we discussed previously, this just involves dividing each vector by its length. The process we described is formally known as the Gram-Schmidt process. Now, let's practice all of this by doing an example in R3. This will be the basis we'll be starting off with. We will start by making them orthogonal. We will let our first vector u1 just be -11, 8, 5. u2 will equal v2 minus v2 projected onto u1. Next, we can use our formula and then substitute in all the vectors. Now, we just need to compute all of this to get our second vector, which is 3, 6, -3. Now, time to get u3. u3 will be equal to v3 minus v3 projected onto u1 minus v3 projected onto u2. Once again, we replace this with our formula, substitute in all the values, and then solve for u3. This gives us the vector 6, 2, 10. To check our work, feel free to take the dot product of any of the two vectors to see that they're orthogonal. All that is left to get an orthonormal basis is to normalize our vectors. For each vector, we divide it by its length. And now finally, we have gotten an orthonormal basis. Visually, we can see that this is an orthonormal basis by putting a unit cube with one corner on the origin. We see that we can rotate the cube so that the tip of each vector lands on a corner of the cube. Many of you might be wondering, why go through all this trouble when there already exists the standard basis, which is already orthonormal? Well, the standard basis is not always orthonormal. For example, in the vector space of polynomials, the Gram-Schmidt process can help us there. Let's say we are working on the space of polynomials of degree at most 3. If you try to do what we did previously, you will see that there is a problem. You can't take the dot product of two polynomials. Thankfully, all we have discussed previously can be defined more abstractly, with the use of the inner product. An inner product is a function which assigns a value to every pair of vectors with the following properties, where x, y, and z are vectors and c is a scalar. The inner product is written like this, where u and v are vectors. The dot product is actually just an inner product for Rn. There are also many other inner products you can define on Rn, as long as they follow these properties. We can even define inner products on spaces other than Rn. Now, we need to find an inner product on the space of polynomials. One inner product we can use is for two polynomials p and q. We will have the inner product be the integral of their product from -1 to 1. Feel free to check that this satisfies the properties we discussed previously. Now, for our projection formula, we will replace the dot product with the inner product. Using this, we will be able to orthogonalize our basis. Now, let's get back to our example. The first polynomial, u0, will be 1. Our second polynomial will be x, minus x projected onto 1. Now, we will use our formula, but remembering to replace the dot product with the inner product. As it turns out, x is already orthogonal to 1, so our vector didn't change. Next, we repeat this for x squared. It will be x squared minus x squared projected onto 1, and x squared projected onto x. Working this out, we get x squared minus 1/3. Finally, for our last vector, we will take x cubed minus x cubed projected onto 1, projected onto x, and projected onto x squared minus 1/3. These two are 0, so in the end, we get x cubed minus 3/5 x. Now, we have gotten an orthogonal basis. Time for normalization. Right now, we have really nice polynomials, and if we normalize them, we will get a mess of square roots. So here, we will try a different way of normalization. We will scale each polynomial such that it will equal 1 when we evaluate it at 1. To do this, we need to divide our polynomials by their value at 1. Now, we have our new basis. What we have rediscovered are known as Legendre polynomials. These polynomials actually go far past 3 and are defined for any n. Legendre polynomials have many applications all through mathematics. So, that is how you can take any basis and turn it into an orthonormal one. Also, I would like to mention once again that orthonormal bases have many more applications which I didn't mention in this video. I wanted to keep the focus on how to get an orthonormal basis. This is it for now. See you later.